Up to now, we discussed about Hertzian dipole antenna, and we said these are fixed antennas, but in practice, we can say Hertzian dipole antenna to be an antenna whose length is less than lambda by 50. And if we have this type of antenna, the power radiated by this antenna is very small, so it has no practical application. So now let us consider antennas which have practical application. These are called the standing wave antennas. They are very practical antenna. We use them in practice. The antennas that we use, the linear antennas that we are using, they are all under this category, standing wave antenna category. These are very practical antennas. The current distribution along on the antenna length gives you a standing wave pattern. So the current distribution will be giving a standing wave pattern, which is similar to an open-ended parallel wire transmission line. Standing wave we get in the parallel transmission line. If it is terminated in open circuit, then we get a reflection from the open end, and the reflection and the incident, when they interact with each other, they give a standing wave pattern. So a standing wave pattern is established along this transmission line. Similar thing happens here in this case. This is a practical antenna. Current distribution is a standing wave pattern. Now look at this antenna. On the right hand side, the antenna extends along the z-axis, and length is from minus L by 2 to L by 2. Let us call L by 2 is equal to H. So I will change that. Sometimes I will call it H, or sometimes I will call it L by 2 during our discussion. This is fed. The energy is fed into this exactly at its center. So since this is exactly fed at center, this is called a center fed antenna. So this is what we are going to discuss is a standing wave antenna which is center fed. So we will be considering a center fed standing wave antenna. Example is a very common example is a half wave dipole antenna which is center fed. Length is L is equal to lambda by 2. So L by 2 will be lambda by 4, and IZ will be of the form I sin k L by 2 minus absolute Z. This we have discussed in the beginning. The current distribution on a standing wave antenna will be of this form. IZ is equal to I is the peak current, then sinusoidal variation, and k L by 2 minus Z. K is equal to 2 pi by lambda. So let us start with finding the radiation vector of this antenna. As we know, our radiation vector you can find out once you find out what is Fz. So Fz theta will be minus H to H. H is equal to minus L by 2. Sorry, H is equal to L by 2. So integration minus H to H. I is the peak current, sin k L by 2 minus Z dash absolute Z dash exponential j k Z dash cos theta dz. Now we have to integrate this. I is a constant that we will take out. So what is remaining is that part we have to integrate. That is of this form, sin a plus bx, where a is equal to k L by 2, b is equal to k, x is z dash, then into exponential cx, c is equal to j k cos theta. So if you put that, this integration will give us exponential cx by b square plus c square into c sin a plus bx minus b cosine a plus bx. This you get from the integration table. You have to remember this integration. Otherwise, you have to go for numerical integration. Using these values of a, b, and c, a is equal to k L by 2, b is equal to k, c is equal to j k cos theta. If you use those values in the integration, then Fz will be 2I by k cos of kh cos theta minus cos kh by sin square theta. That will be what is Fz. Once we find out Fz, we will find out the normalized gain. Once we find out radiation vector, we can find out normalized power gain. remember the radiation vector Fz. Then we have to find out intensity, then power gain. So intensity U theta is equal to eta k square by 32 pi square I Fz absolute square sin square theta. Fz, we know what is Fz expression. So put that expression here. So that will give us eta I square by 8 pi square into cosine kh cos theta minus cosine kh by sin theta whole square absolute whole square. So once we know this, then we can find out what is the normalized power gain. Normalized gain is such that the intensity, the amplitude of intensity becomes 1. So G theta is equal to U theta by U max. We have to find out what is U max. So that we can write as G theta is equal to Cn. Cn is the normalizing factor. Cn into cosine kh cos theta minus cosine kh by sin theta absolute of that square. So that into Cn. So Cn is the normalization constant. So if you multiply Cn with U theta, you get the U max. So this will maximize G theta to unit. This depends on the length L and this may not occur. If you look at this may not occur. R theta is equal to pi by 2. What in case of Hertzian dipole, Cn the maximum was occurring at theta is equal to pi by 2. In this case, it may or may not occur at theta is equal to pi by 2, depending on h. Now, if you are in the limit L goes to 0, which is again we are going to Hertzian dipole. In that case, G theta is equal to sin square theta in that limit. Otherwise, if you are not in the limit, but you are beyond this, but L is small. L is not going to 0, but L is small. When for small values of L, as you know, sin x by x is equal to 1 for small x. So sin x is equal to x. Use this. If you use this relation sin x is equal to x for small values of L or small h, we will get the current. Now the current will be Ij is equal to I into sin k L by 2 minus absolute z. Now sin x is equal to x. So for that we will put I k L by 2 minus absolute of z. So that is for z less than minus L by 2 to less than L by 2 in that region. So minus L by 2 less than z less than L by 2. So this, if you look at the current, this is like a straight line. Ij distribution is like a straight line. So it goes up, then comes down. So it is like a triangular distribution over the antenna. I have discussed this already. When z is equal to 0, this is maximum. When z is equal to plus minus L by 2, this is minimum. So at both the ends, it will be 0. At the center, it will be maximum. It increases linearly from 0 to maximum, then decreases linearly from maximum to 0. So at two ends of the antenna. So you have got a linear current case, in this case small variable. So this type of antenna where this approximation holds good is called a small antenna. This is when your length is greater than lambda by 50 but less than lambda by 10. In that case, this is called a small antenna. Okay, now let us consider what will be the radiation resistance. To find out radiation resistance, look at the current distribution. So we have the antenna and you can see different current distributions for different lengths of the antenna. Different length means physical length remains same, but frequency changes. Frequency changes means lambda changes. Lambda changes means electrical length changes, which means physical length L by lambda, that is the electrical length, that changes. So for different lengths, you can see for different frequencies, in all cases at the end, the current is 0. But not in all cases at the center current is 0. At the center, you can see if it is less than lambda by 10, the triangular distributions are for less than lambda by 10 distance. But if it is lambda by 4, or if it is say lambda by 2. If it is lambda by 2, you can see the violet distribution. The violet is at the left end it is 0, then there is a half wavelength variation, at the right end it is 0. So there is a half wavelength variation with peak at the center. Then if it is L is equal to length is lambda, which means total length is lambda. So each side is lambda by 2. So you can see this red distribution, which is 0, then goes to peak at the center of the arm, then comes to 0 at the center of the antenna, then goes to peak at the center of the arm, then goes to 0. So this way this is, so it is 0 at the center of the antenna. Current is 0 at the center of the antenna. Similarly, if lambda it is 2 lambda, then current is 0 at the center of the antenna. So it is not always true that the antenna at the center of the antenna current will be maximum. If current is not maximum, current is 0. Current is 0 occurs under one condition, that is it is open circuited, impedance is infinite. So it is open circuited. Current is 0, is it is open circuited or it is infinite at the center. So that is the condition under which there will be the 0 will occur there. But that does not mean that antenna will not radiate. Antenna will radiate. So radiated power radiated in terms of the peak current. Peak current is a maximum at some other point, not at the 0. So in terms of peak current, we can say P rad is equal to 1 by 2 R peak. R peak is the peak resistance into I square. I absolute is the current distribution. So I square. Similarly, input current at the input, in terms of the input current, we can say P rad, radiated power, is equal to 1 by 2 R in into I in square. R in is the input resistance, I in is the current at the input. So when that is called, the I in is not available to us if I in is equal to 0 or I in is equal to infinity, then we use the peak current, otherwise we use the input current. Every time we can use both of them are same. P rad is equal to same in both the cases. So now let us define or find out a relationship for P rad. P rad is equal to 1 by 2 R peak I square and P rad is equal to 1 by 2 R in I in square. Equate these two. If we equate these two, then for a general dipole, we will get that a general dipole of length L, I in is not necessarily equal to the peak amplitude I. So I in, actually I in is equal to I0, because at Z is equal to 0, you are finding the I in. So I in is equal to I0, that you can write as I sin KL by 2, because Z is equal to 0, then sin K into L by 2 minus absolute 0, absolute 0 is 0, absolute Z is 0, so sin KL by 2, that leaves us at that. So you can write I in is equal to I is the peak current into sin KH, because L by 2 we are taking H, so that is sin KH. I in is equal to I sin KH. From that we can say that R in is equal to 2 times P rad by I in square. So put that 2 times P rad by I in square. For I in we will write I sin KH. Then for P rad we will write 1 by 2 R peak by I square. If we do that, then R in is equal to R peak by sin square KH. So this gives us a relationship between the input resistance and peak resistance. This is the relationship. Now you can find out what is P rad. P rad is equal to integration of intensity over the solid angle. So integration u theta d omega, that is equal to eta I square by 4 pi integration 0 to pi cos pi h cos theta minus cos kh absolute square divided by sin theta and d theta. So now I'll find out what is R peak. R peak we will find out once we know what is P rad. We can find out what is R peak is equal to period by I square. So it will be eta by 2 pi integration 0 to pi cos kh cos theta minus cos kh whole square divided by sin theta d theta integration of over theta. Then delta omega, we know it is integration over pi from 0 to integration over theta from 0 to pi, integration over phi from 0 to 2 pi, g theta d omega, that is what is delta omega. Okay, that we can write as 2 pi into Cn. For g theta we can write g theta is equal to Cn, then put other R peak value. So using that we will get cos kh cos theta minus cos kh whole square by sin theta d theta. So from that we will get this is equal to 2 pi Cn into 2 pi by eta into R peak. So if we do that, then we have found out delta omega, then find out d max. D max is equal to 4 pi by delta omega, that we can find as 1 by Cn into eta by pi R peak. So d max is the directivity, maximum directivity. D max is the maximum directivity. We have found out this expression. Now for a standing wave antenna, if we plot the radiation resistance or input resistance versus normalized length, that is shown here in this graph, as well as we plot the directivity in the d max in dB. So that is shown in this figure. If you look at this figure, the dashed curve, green dashed curve, is for the R in. The blue curve is for the R rad. Now compare those two, R in and R rad. This is slightly, this curve is slightly mistaken. There is a small mistake in this curve. The x-axis should shift by an amount of 0.5. So that is the problem. So there is 0, actually the point 0 should be 0.5. Beyond that, on to the left there is a 0. On this somehow I have made a mistake in putting the values there. Anyway, so if you look at this, these two curves, R rad and R in, they follow each other in the beginning. So they are same in the beginning. In the beginning means when you have Hertzian dipole, in that part they are following each other. The dashed curve and the blue curve, they are following each other. So that part is not useful to us. Then when it is 1 lambda, when it is lambda, this is actually open circuited. It appears to be open circuited, so impedance becomes, input impedance becomes infinity. So that will be 1. When lambda length, for lambda length, length of the antenna equal to lambda, we have seen that it is 0. At the center the current is 0, so that should be 1. So 1 should be at 0.5 should be 1. Anyway, so that should be 1. So that is infinity there, because current is 0, so input impedance is equal to infinity. Current is 0 means impedance is infinity. So input impedance is infinity. So that shows that. Then if you come to the directivity, directivity is increasing gradually from 0. It goes to maximum at 1.25, then comes down to a lower value, then goes increases. Which means if you increase the length, the directivity will increase up to a certain point, then it will decrease, and then that value, the values where it decreases is of no use to us, because their higher order modes comes in. They are not going to contribute. We will see that later. So the maximum value we will see is 1.25. So length is equal to 1.25 is the best choice. So when we are designing this, so let us see another way of looking at this. So length is equal to 0.5 lambda, which means lambda by 2. When length is equal to 0.5 by lambda, you can see that we have got a figure of 8 radiation pattern. D is equal to 2.15 dB. So that is the directivity. Then if we increase the length to 0.75, then directivity is increasing, so it becomes narrower. Figure of 8 becomes narrower, which means directivity is increasing. That becomes 2.75. If we increase that to 1 lambda, directivity is further increasing. You remember that curve, it is gradually increasing. So 1 lambda, it is further increasing. So that becomes 3.82 dB. Now we further increase the length to 1.25 lambda. There you can see directivity has further increased, become very narrow. The directivity is 5.16 dB. Now there also you see an interesting thing, that in between the two main lobes, the smaller side lobes are starting to appear. So we are getting side lobes. With the main lobe we are getting side lobes here. Now if you further increase it, you can see that main lobes become useless. They are becoming like a side lobe. Other lobes, side lobes are becoming prominent. So prominency of main lobe is lost. So going beyond 1.25 lambda is not advisable if you are considering a radiation pattern that you require a figure of 8 radiation pattern, omnidirectional radiation pattern. When we require, we do not require L to be more than 1.25. So 1.25, 1.75, and beyond that, the radiation pattern actually is degenerated, and you are going to get a conical pattern instead of a figure of 8 pattern. So those are not required. Because of the current distribution, you get this. So these are not required. Although you get high directivity, they show high directivity, they are not required because their directions are not proper. They are in undesired direction. The beams are in undesired direction. So here we will take a break. We'll come back and discuss about half wave antenna in about 5 minutes.